Omnidirectional reflection characteristics of photonic crystal for optical communication. Abstract: in photonic crystal it is possible to change the reflection characteristics by various methods. In this paper initially one material is kept constant and the second material is varied to observe the reflection coefficient. Then the number of layers is varied to observe the reflection coefficient. The reflection coefficient is expected to be unity. Effect of change in the dimension on the property is observed. The reflection coefficient, stop band, and center frequencies are calculated. Introduction to defect in the perfect periodicity results in change of behavior in the transmission of different wavelength. Response of the crystal for a single defect and double defect is observed and graph is analyzed. Under certain condition, one-dimensional dielectric lattice displays total reflection of the incident light. The parameters are carefully chosen for better reflections which will find application in optical communication as switch, mirrors, sensors etc. Keywords: photonic crystal, stop band, reflection coefficient, transmission coefficient. Introduction. Photonic crystals are constructed by using alternating layers of high and low value of dielectric materials. Two materials with refractive index N1 with thickness A, N2 with thickness B, D equals A plus B called lattice constant are used to form a photonic crystal. When different frequencies enter photonic crystal depending on the dimension and dielectric constant, it allows certain frequencies and blocks other frequencies. Allowed wavelengths that propagate through the crystal form a band called photonic band or pass band. Group of wavelengths that are blocked from propagating through the crystal form a photonic band gap, PBG, or stop band. Light propagating in a high dielectric material is reflected at the interface of low dielectric material. A periodic potential exists due to dielectric media. Multiple reflection and refraction occurs at each interface. For one-dimensional photonic crystal, the variation is only in one direction. Each of the plane reflects only a very small fraction of incident plane wave. The total scattered wave consists of a linear superposition of all these partially reflected waves. The diffracted beams are found when all these reflected waves add up constructively. 8. Let be lattice constant, which is the period of index variation in space. The path difference for rays reflected from two adjacent planes is 2. Sin O, where O is the angle of incidence measured from the planes. Constructive interference occurs when the path difference is an integral number of wavelength /n in the medium, so that 2 sin O equals m, n, m equals 1, 2, 3. Where n is the averaged index of refraction of the periodic medium and m is an integer. Beam diffraction occurs for certain values of O which obeys the Bragg's law so that reflections from all planes add up in phase. 2k sin O equals m, 2p/. Where k is the wave number of the light beam in the medium, k equals 2pn/. The term 2p/ is known as the grating wave number. The photonic band gap occurs at K equals mp. If W0 is the center of photonic band gap such that K1A equals K2B equals p/2. When the frequency of incident wave falls in the photonic band gap, the block wave generated in the periodic medium is known as an evanescent wave which cannot propagate in the medium. The electric field amplitude decays exponentially. Thus the energy of the incident beam will be totally reflected and the medium acts as a high reflectance mirror for the incident wave. The reflection coefficient can be made 1 by proper designing of the photonic crystal. 10. 2. Literature survey. The omnidirectional reflection characteristics of one-dimensional photonic crystal with the first material as silicon dioxide with refractive index 1.5 and the second material as germanium with refractive index 4. The thickness is taken as 600 nm and 400 nm respectively with the number of layers as 10. It is clear that the common range of unit reflectance is from 2247 nm to 2438 nm. So that total omnidirectional reflection range has the bandwidth of 191 nm1. A defect in the otherwise periodic photonic crystal can be introduced to alter the properties of it. The two materials chosen are Si and air representing Na equals 3.45 and Nb equals 1 and Da equals 0.2a, dB equals 0.8 A respectively, where the parameter is the lattice constant. The defect material is taken as silicon and its refractive index is varied between 2 to 4 at the given wavelength of 1550 nm and the thickness is taken as 0.4 A. The change in refractive index can be obtained through changes in pressure, temperature, or concentration of impurities in SI. The stop band and pass band can be controlled by changing the dielectric constant and the dimensions of the defect layer. When the refractive index is increased, the stop band shifts to the lower value. This is used for making filters. The photonic crystal can be made from graphite with low dielectric constant and tellurium with high dielectric constant. The value of refractive index of graphite is taken as 2.87 and the refractive index of tellurium is taken as 4.6 respectively. The thickness of each layer is calculated by quarter wave stack condition d equals 0.0/4 n, where 0.0 equals 800 nm, which is the central wavelength, and n is the refractive index of layer. So the thickness of graphite film is taken as 69.68 nm and that of Te is taken as 43.47 nm. The number of layers for computation is taken as n equals 20. Hence the totally reflected wavelength band, which is common to the both polarizations and for the entire incident angles, lie from 885 nm to 697 nm, which gives a significant omnidirectional reflection band of 188 nm. This narrow omnidirectional reflection band in near-infrared region of electromagnetic spectrum makes it suitable for making near-IR cut-off filters, which can be used in digital cameras and other imaging sensors. The effect of number of layers is studied, and it is found that as number of layers increases, the band becomes wider for the same refractive index contrast and the reflection coefficient approaches unity. 3. In this, a photonic crystal with Si as high refractive index material and SiO2 as low refractive index material is considered. The refractive index of both the materials has been taken as wavelength and temperature dependent. So the allowed bands can be tuned by varying the temperature without changing geometry and angle of incidence. The refractive index of SiO2 layers are increase more per degree of temperature in comparison of Si layers. So refractive index contrast is decreased with temperature. The property of the proposed structure can be employed to tune the ODR bands. The refractive index of these two materials is temperature and wavelength dependent. Therefore the variation in the refractive index can be used to tune the allowed bands. The thickness of both layers is taken to be equal. This type of filter can be used in many optical devices such as temperature sensor, wavelength demultiplexer, etc., and in other optical systems. By choosing appropriate values of temperature, we can design a frequency selector or rejector. Also, by cascading 2, 3, or more filters, we can design a perfect mirror or monochromatic 4. In the construction of photonic crystal, 3 materials can be used with silicon dioxide with dielectric constant 1.5, tellurium with dielectric constant 4.6, and germanium with dielectric constant 4.2 for the stack of layers. Lattice period d is taken to be 400 nm and the thickness of A and B layers, A and B, are taken as 0.8 d and 0.2 d respectively. But for the stack of NC layers, A1 and B1, are taken as 0.7 d1 and 0.3 d1 respectively. By choosing appropriate values of the controlling parameters, refractive indices and lattice period, of the AC layers, it is possible to obtain the desired ranges of ODR region 6. 3. Methodology. The structure is made up of alternate layers of materials with high and low dielectric constants. The input signal contains all the frequencies. Depending on the thickness of the layers, dielectric constants, number of layers, the output signal will contain only the permitted frequencies. The remaining signal reflects back towards input. In stop band, the wave gets reflected. Fig 3 indicates the amplitude level. Red color indicates high amplitude and blue color indicates low amplitude. When the signal is outside the band gap, it gets transmitted as shown in Fig 4. Alternate layers of different dielectric materials are taken. The first material is kept constant as silicon dioxide, SiO2, with refractive index 1.45 and the second material is changed. The different materials taken are Al2O3 with refractive index 1.76, ZNO with refractive index 1.92, SiC with refractive index 2.55, TiO2 with refractive index 2.65. The combined result of reflection coefficient is as shown in the figure. The center frequency which is selected is 1550 nm, which is optimum for optical communication. So the structure can be used as switch or reflector in optical communication. The following table gives the center frequency obtained from the graph for different combinations and the corresponding bandwidth. It is observed that the combination of silicon dioxide, SiO2, with refractive index 1.45 and the second material as silicon carbide with refractive index 2.55 gives the best result with center frequency 1525 nm and bandwidth of 550 nm. So for further analysis this combination can be taken as the reference. 4. Conclusion. In the structure of photonic crystal, initially one material is kept constant as silicon dioxide and the second material is changed to Al2O3 ZNO SiC and TiO2 to observe the reflection coefficient. As observed from Table 1, the combination of silicon dioxide and silicon carbide gives best reflection with center frequency 1525 nm and bandwidth of 550 nm. The number of layers in the crystal is varied and it is observed that the reflection coefficient reaches to unity as the number of layers is increased. From Table 2 it is seen that when 15 layers are used the reflection reaches to 99%. Next, it is checked to see if there is any variation with dimension ratio. When the dimension ratio of each layer is varied there is slight shift in the stop band. Any combination can be taken as long as the reflection coefficient is near to unity. Center frequency is near to the designed value 1550 nm when the dimension ratio is equal. When periodicity is changed, a defect gets introduced. When the defect is at the beginning, the side bands are reduced. When two defects are introduced, the bandwidth is slightly reduced. Thus we can design photonic crystals for reflecting any wavelength by properly designing the materials, the number of layers and the thickness of each layer.